Cool. So should we recap what we did last time? I can maybe summarize in case you didn't listen what we were talking about. Was an animated GIF that was posted on Reddit asking essentially how it worked. And it showed a cylinder of water, maybe like a foot tall, maybe like the size of a cross-section area of a quarter, maybe a little bigger than that. And then inside was an hourglass, just like a normal sand hourglass. And it started with the hourglass at the top with all the sand in the bottom half of the hourglass. That's how the image started. And then the cylinder was flipped over, putting the hourglass on the bottom. And it stayed on the bottom for a little while until a certain amount of sand poured into the bottom half of the hourglass, which was empty after being flipped over. And then all of a sudden the hourglass started to float up to the top. So the question was, how does that work? Like, what's happening? So last episode, we spent a good deal of time trying to figure it out and basically arrived at what I thought was kind of an unsatisfactory answer, that it was getting stuck on the sides of the cylinder of water, whatever was holding the water, because basically the empty half being on the bottom causes the hourglass to want to flip over so that the heavier sand half is on the bottom, as it was at the start of the GIF. And that like wanting to flip over leads to a torque, which kind of wedges the hourglass up against the sides and prevents it from floating up until there's a point where there's not as much torque and it's not pushing against the side of the cylinder of water, at which point it would be able to float up because it's not pressing against the sides. So that was my kind of reading of what happened. And then Zach, what did you try to surmise?
Well, so the question I wanted to answer is, I just said, let me try modeling this first as a simpler case and then building up to this actual hourglass thing. So I said, I'm going to start with like what would happen to two separate cans or two separate, buckets or something in water submerged. But the only thing that's like linking them together is the mass that's in them. So you can only transfer mass from one bucket to the other bucket, and that's it. And then so when you do that, what happens essentially was the question I was wondering. And that led us down this rabbit hole that essentially led us to an intuitively wrong answer. And, it's good that it was intuitively wrong because our answer was wrong, or well, my answer was wrong. Essentially, the thing that was wrong with it is it seemed to say that as mass moved from the top to the bottom, that you would have the net force, meaning the force on both cans, would change. It would go from, like a down force to an up force. But, Newton's laws kind of say like, well, we can just treat everything as a point. And if we treat both cans as a point, then it shouldn't matter where, that we're moving the mass back and forth. The net force is going to be the same no matter what. And that's what was intuitively wrong, is that we said the net force is changing just because we're moving mass between the system, but it shouldn't change on the whole system. So something was wrong there. And then I went back and did more math and showed that, okay, that was totally wrong. We ended up with just a math circle. But I went ahead and like wrote made a simulation that we're going to post that you can check out of this system and kind of describing what happens with it. But I wanted to then know, once we said, okay, like this is a fruitless path, I wanted to know, okay, well, let me look at the real system, a object, two containers attached together, so their forces interact with each other. So the bottom can will push on the top, or the bottom half of the hourglass will push on the top half, and the top half will pull down on the bottom, or some combination of that. There's a force interacting between the two now. And once you do that, you get right back to the great equation, F equals ma, where it doesn't matter where the mass is in the system, the force is the force, and that's good. That's what we ended up with. And so I think that leads us to say then, your answer has to be the right one.
Yeah, I think so. I tried working out from Newton's law, if we considered two separate halves, and had some restriction on the way the masses worked together. They had to always add up to the same amount. And I always just came back to the fact that you should treat it as one object. It doesn't matter if it's one half and another half. If the entire object's density is less than the water, it'll float just like you'd expect. And if the entire object's density is greater than the water, then it'll sink just like you'd expect. So there was no way to separate them out and say like, oh, when there's 80% sand in the bottom, then it floats versus less than 80% or something. There wasn't some turning point where it would change from being able to sink to being able to float. It just didn't happen. There was no way to find that. So
yeah. So it turns out actually, so I looked into it a little bit, that this is a Martin Gardner puzzle. And I don't know too much about Martin Gardner other than he's pretty famous for writing puzzles for, I think it was Scientific American.
Okay. Huh.
Where he had like a lot of like matchstick puzzles. He's a mathematician. I have his Wikipedia open right here. I won't read you too much from it, but yeah, he was a mathematician and he wrote essentially a lot of these puzzles for 25 years he was coming up with like mathematical games and stuff. So it's kind of famous, these puzzles. And so he wrote this in a book that he wrote called Mathematical Carnival. It's on
Mathematical Carnival?
Yeah.
There's a famous physics book of puzzles called The Flying Circus of Physics. I don't know which one was first or second.
I think he might have wrote that one too, I wonder.
Oh, really?
Or maybe not flying. I thought he did have another circus-related one too. But essentially, this book is on, you can borrow it from archive.org, which is a free library online. So on page 174, it shows a picture of it and describes what's going on. You can also look up the GIF, but the answer's in there. And here, I can just read you, what he said. He said, when the sand is at the top of the hourglass, a high center of gravity tips the hourglass to one side. The resulting friction against the side of the cylinder is sufficient to keep it at the bottom of the cylinder. After enough sand has flowed down to make the hourglass upright, the loss of friction enables it to rise. And then it also goes on to say you can actually do this in reverse. You can have it sink. So it starts off at the bottom. The hourglass does, and when you flip it, it'll sink.
Oh, I see.
After some period of time. Just so what all that matters is the density slightly higher or slightly lower than water.
Right. Yeah, that makes sense. I'm curious if he just like came up with this puzzle in his head, because I wouldn't trust the physics enough to just say like, oh yeah, this is clearly going to happen if you design an hourglass in a tube like this way. Or did he see it somewhere and then write the puzzle out?
So
or did he build it?
He actually says in here, let me see if I can find it. Shops in Paris carry this toy, both versions of it, and in a combined version where it has both cylinders in it. And it says, the toy was said to have been invented by a Czechoslovakian glassblower who makes them in a shop just outside Paris and is usually more puzzling to physicists than other people.
Got it. Yeah, because I wouldn't just like imagine this thing and then be like, oh yeah, that's clearly what's going to happen. Like without actually like... I would have expected the thing to have been built first and then the puzzle written out afterwards. Yeah. So that makes me feel better.
Yeah. So it sounds like someone built it. And there's another paper referenced in there called The Weight of an Hourglass by Walter P. Reed in the American Journal of Physics, Volume 35, April 1967. Pages 351 through 52 if you want to read a paper on it.
Wow.
Just to add a little bit more, and I'll put this in my post about this too. So I was curious, if this is going on, can we come up with some formula that predicts the amount of sand that's in the top and in the bottom when it wants to float up? Because when we looked at it, I think last time we said there's roughly, it was like 75, 25 or something. We said when it was 25% empty.
Yeah, when the top is 25% empty, is that? I thought it was when 25% of the sand has fallen into the bottom hourglass, then it started to float up.
Right, yeah. And so I wrote out an equation that kind of just said, let's track the center of mass as the sand is falling, right? Because that's the thing that's changing, and that's what's applying this torque. And so I looked, okay, when does the center of mass hit the center of the hourglass, that where all the sand is falling through? And at that point, the net torque is 0. So it's going to want to float, or after beyond that point, it's going to correct itself. So when I did that, I ended up, and I think it was roughly 76%. It's the level of the sand was 76% of its original level, or 25% of it has gone down.
Right.
So I think that was a fair,
and we were just eyeballing that, like about a quarter of the sand had fallen down, and then the calculation came out to pretty much exactly that, which is pretty cool. Yeah.
And I just did it by, the 25% isn't by like mass. It's by, if you look at the height of it, it looks like, the height of the lower one is 25% of the original height.
Right.
And that's what it kind of worked out to. So that was kind of cool.
Cool. So what's up for this episode?
We're going to answer Reddit users' standby for rant question. He posted on Ask Science, what percent of my weight am I actually lifting when I do a push-up?
Okay. So what I'm thinking is it depends on a few things. Like imagine doing, I don't know what it's called, a vertical push-up, or like I don't know what that's called when you're up against a wall, like a handstand basically, and then do a push-up. Like that is 100% of your weight, right? Like that's got to be the hardest situation.
Yeah, that's like Goku level push-ups.
And then imagine standing with your feet on the floor up against a wall and pushing. Like that's not really a push-up at all. It's 0% of your weight. Like, yeah, you have to exert a force to accelerate your body away from the wall, but you're not pushing against gravity, right? So we got like this continuum of amount of force required to work against gravity, if that's what we're saying is what percentage are we lifting. And then if we go to what I'm guessing this person's expecting is your feet and your hands are at the same level, like a normal push-up on the floor. So, and the reason I wanted to say that is because I think it'd be important to be like, oh, if it ends up that like short people don't lift as much weight as heavy people, or as tall people, or light people are just light, and so they're doing less work than someone that's a heavy person, you can affect this by adjusting the angle. That's why I wanted to say that from the start. So
so there's a whole, the max you can do is your own weight,
right? And
the minimum you can do is nothing,
right? So yeah, so don't worry if you're like, oh, I'm a short, very lightweight person, I'm never going to be bulky from doing push-ups. You can change the angle and affect how much you're actually lifting, I think. Or you could just have somebody sit on your back. But yeah. So let's go with the like standard, how much am I lifting if my feet are on the floor and my hands are on the same level? And I'm starting from like a horizontal position and then push up. How much weight am I lifting? So I haven't thought about the answer. I only went to those limits of the angle dependence.
Well,
it's not 100% of your weight. We can agree that that's true because your feet are holding up some of your weight, right?
Right. Yeah.
Yeah. And I think the question is asking if you flipped on your back and then held a weight over your chest and pushed it up like a bench press, what weight would it be equivalent of a push-up, right? Is that essentially the question?
Yeah, I think that's a fair way to put it. Yeah. If you're gonna do the inverse, you have to lift weights now inside of your body. Yeah. How much would it be to mimic a push-up? Copy it.
Right. So let's go with, let's say you're only supported by your toes and your palms of your hand. Like those are the, like, I know it's 4, but let's say it's the 2 supports that are holding up your entire body weight. And if you were completely symmetrical, meaning like your weight was evenly distributed across your entire length of your body, then each would be holding up half your weight, right? Your hands and your legs.
Right.
And then if you did a push-up from there, would it be the equivalent to lifting half your body weight? That's my quick and dirty reasoning. Like just super simplifying. We'll get to like distribution of weight of your body probably in a bit, but just if you're uniformly distributed and you lift it up with the front support, you're lifting up half the weight, right?
Let me see if I can kind of give a different version of what you're saying. Like imagine, I think this is kind of saying like, okay, imagine you were a dog, right? You're on a dog. Oh, a dog. Yeah. You're on all fours, and I feel like a dog is a little bit more, you can imagine it being a little bit more evenly distributed and you go down and come back up. Is that's then, that would be your full weight, I guess, right? If you were squatting as a dog, but then if you were just to go down with your front legs and come back up, is that half now?
I mean, I think roughly, yes, but there's going to be slight variations because it's not just vertically up and down, right? Like it's kind of like you're also shifting forward and backwards slightly, right? I don't know how precise we want to be. Like my answer is half to start with, but then it's more fine grained than that because people have more weight on the top half of the body maybe than the bottom half. But and then I think there is a slight shift like forward and backwards. Like if you had like Inspector Gadget arms, like Go Gadget arms, and you went really like extended them very far, then your weight is now more on your feet than it was before. So your hands, like every inch you lift when your arms are very long is less of a push-up, more getting into standing vertically against the wall.
Right. Yeah. So like I wanted to say that like half is a decent starting place, but it can't be the right answer because like you started off saying, there's a range from your full body weight to nothing. And the only thing that's changing between those two is your angle.
Right.
Not, you're not getting lighter. So when your explanation of it just being half, we haven't begun to take into consideration the angle of it.
Right. So rough numbers, it's half. And then as you push upward, it gets a little bit less than half. Assuming you're uniformly distributed, like your mass throughout your body. Is that good so far?
Okay, wait. So it's half and then what? Sorry.
It decreases from there. As you do the push-up, you're lifting less weight because you're approaching the standing up against the wall situation, which is the zero weight.
So that's starting from the down position. We need so we have the down.
Starting from your weight is supported by your palms and your feet, but you're down, and then you start the push-up. And you're lifting half your weight, but then it kind of starts to decrease as your arms get longer and longer.
So I think especially when you're in the down position, I think, half is a pretty good answer, especially if it's the case that your body is completely horizontal in that position.
Right. Yep. So half and then a little bit less than half. So if you wanted to do a bench press, take half your weight and then maybe, I don't know, take off a kilogram or something. It's not going to be that much different, right? The angle is pretty small.
Right. Yeah. I mean, I think we could kind of figure it out if you model yourself just as a triangle and you look at, vectors, your decomposition of your forces.
Yeah. But then I think probably a more like probably a greater effect than the angle that you're making with the floor and how that affects how much weight you're lifting is your distribution of mass. So that's up to you to figure out, are you more top heavy or are you more bottom heavy? Like, do you have like big, broad, bulky shoulders or do you have like huge, massive legs because you're a cyclist and you never lift like weights at all with your arms? So that, that's on you to figure out how you want to adjust that. So it's a sliding scale, whichever way you want to go.
Well, I think for most people, their center of mass is roughly around their belly button.
And that's above the halfway point of their height, right?
For me, it is. I measured.
I think that's true for most everyone. When would that not be true? Someone would have really short legs.
Yeah.
Oh, so now, yes. So someone with short legs, would you be lifting less than half your weight or more?
Well, if you have really short legs, So, okay. I think we're kind of saying in the down position, it's always half. If you're horizontal, your body's horizontal.
Right.
Okay. So, but then if you have short legs, as your arms go up, your angle is going to be steeper.
Oh, right. So it gets even weaker. Like it's less of a force to do the push-up if you have short legs.
Yeah. Can we...
Yeah.
Sorry.
As you increase the angle.
Yeah. I was going to say, can we really quickly figure out, okay, what's the relationship if it goes when you're standing straight up, or like kind of like you were saying, as your go-go gadget arms get really, really long, more of your weight goes on your feet. Then as you go flat, it goes to 2. So is that that's a arc tangent?
Well, let's define our angle. I think the angle is between the floor and your body, right? So when you're horizontal, the angle is 0.
Yes. Okay.
Is that right? And so that's the maximum. So it's like a cosine, I think. And then when it's 90 degrees, like you're standing up vertically, feet on the floor, it's 0. Oh, no, it's something, there's like a half angle because so it goes from, if the angle is 90 degrees, the force is 0, right? If the angle is 0 degrees, the force is half your weight. And if the angle is negative 90 degrees, which is the handstand situation, your force is 100% of your weight, right? So that's like negative 90 is a force of 1 times your weight. 0 is a force of a half of your weight. And then 90 is a force of 0. Does that make sense?
Yeah.
So what function does that?
Well, yeah, I think you were right with some sort of cosine, right? Well, okay.
I think it's negative sine theta over 2. No, does that make sense? Or negatives? I have pencil and paper.
Well, we have to have some sort of phase shift, right? Oh, negative. Nope, that doesn't.
No, it's going to be like a half or a double angle or something like that.
Well, because for any cosine, when you're at 0, you're at the cosine's peak. And for sine, when you're at 0, you're at 0 for any sine. So there's got to be some sort of shift in the plot, right? So such that when you're at 0, you're halfway.
Okay.
I mean, that'd be, I mean, because it's...
I see what you're saying. Yeah.
But then, yeah, okay, wait. But then, yeah, okay, well, I mean, the whole function's a little bit, we don't have to get into it. I just kind of wanted to get the general relation. I mean, is it a torque thing that we have to worry about?
I don't know.
Yeah, I don't know. I'd have to sit down and look at it more to for next week, I guess.
Okay, but let's go back. So what were we saying before this?
I think we're going over the range of values that it could take. Okay, so if you're, I mean, I could go back and listen, but if you're, I think we're talking about someone with short legs and what happens to them. Right.
Yeah, so someone with short legs, as they do the push-up, they're lifting more of, or they're lifting less of their body weight as the push-up goes on. Like it starts off with half, just like everyone starts off with half, but then as they do the push-up, they're going to be lifting less weight. Like by the end of the push-up, it's less weight.
Yeah, because their angle is steeper because of their shorter legs.
So what they would have to do if they wanted to do a bench press equivalent would be hold a bucket of water with a hole in it, and everyone's has a hole in it. And as they do the push-up, water is draining out. Or as they do the bench press, the water is draining out of the bucket because they're lifting less weight as they extend their arms.
Yeah, right.
But a shorter person's hole is bigger.
Yeah, that's a good way to put it. Yeah, and it always starts at half their body weight. And now you gotta change because it's changing. So it's like, how much is it changing? Okay, what about just like a tall person versus a short person? I guess, does that matter? So let's say like your arm to height ratio is the same for both of these people.
Oh, because your length of your arms? Yeah, that's right. Are you similar triangles with a short person? Yeah, so if you are similar triangles with a short person, it should be the same for both of them, right? I mean, like their mass is different, so that's different, but percentage-wise of their weight, it should be the same. If the same push-up, like variation across the entire push-up. Yep.
So really, it's only when someone has really long arms or like really short legs or long leg, if you're disproportionate in some way.
Right. A gorilla doing a push-up is going to have a much different change in weight throughout the entire push-up than a normal person would.
Yeah. So like if you're a normal person, I feel like the way you do a push-up, at least, I don't know, okay, I shouldn't say it that way. The way I do a push-up, whether I'm normal or not, that's the different story, is, I start in the up position and then I go down.
Oh, I see.
And then back up.
That's funny. When I think of doing a push-up, I start low and then start like pushing.
So for me though, so I think your way might be better, because if I am at my height, like I'm lifting whatever percentage of my weight, and then I go down. If I don't go all the way down and then back up over that whole time, I'm doing less of a push-up, unless I go down to level 0 degrees. Right.
You're staying at the extended arm. You're staying close to the extended arm region of the push-up more.
Yeah.
Because you never touch the bottom, which is the full most amount of weight you could be lifting during your push-up at the bottom.
Right.
Got it. Yeah.
Yeah. And
go ahead.
That's kind of presuming, and I don't know if people do this or not, I definitely don't, that you could lower your body such that your the height of the from the ground to your chest is like the height of your feet, right? That would put you at 0 degrees. Ground to chest is like the length of your foot.
Yeah,
from toe to shin.
Yeah. Now, yeah. Assuming we're a flat board from our shin to our chest, which I don't know, my knee kind of sticks out a little bit.
Right.
My thigh's a little thicker than my shin.
Being rough with it. So, but I definitely can't go that low.
Oh, huh. I don't know.
Well, maybe I can't lift half my weight. That's the issue.
Yeah. So how about push-ups on your knees? What changes?
Right. Okay. Well, I think that's essentially the short person limit, right? Or not the short person, the short-legged person limit, right? It's I've now shortened my my length,
right? But how would you okay, I weigh 150 pounds and I want to do a knee push-up. How do I know how much I'm lifting in that case? Would you would you figuratively chop off your legs at your knee and then you say, okay, I'm lifting half the weight minus, take my weight, subtract off the bottom half of my legs and my feet, and then you're lifting half that?
I think in theory.
I think so.
But additionally though, in like a more realistic perspective, you're also not going to be able to get down to the 0 point really, unless you're like lying on the ground, in which case the ground is supporting you.
Right.
So you're overall, you're doing, you won't ever get down to the halfway point.
Yeah. Does it make it easier on your knees? Like, the fact that you have your legs sticking out over, like past your knees on the other side, like the lower part of your legs, are they helping you? Like imagine like a seesaw or something like that, like the weight on the other side of the pivot point, is that assisting your push-up at all?
I think it depends, right? I think if you have your legs in the air, they're going to provide some counter torque,
which would help you.
Yeah, but it also depends on how, like the angle between that your knee is making, right? If it's straight, if your knee is straight above your your foot is vertically above your knee, it shouldn't do anything. If it stays that position throughout your push-up,
right?
Because the force is directly above the pivot, no torque.
I guess this gets into like anatomy, which like how does your calf muscle connect to the back of your knee? Like I don't really know if there's any leverage that it's assisting in lifting the front half of your body if you're pivoting at your knee during a push-up. Yeah,
I think the only thing that it could add is some sort of counter, because you're not pulling on any. Maybe if you had like I don't know, if your legs were tied to something, you could provide some sort of counter, even more torque than just their mass through your calf muscles.
Right.
But because that's not because they're just floating there, essentially, the muscle itself can't add anything. There's nothing for it to pull against.
Yeah. So I think the bottom line is you're lifting half your weight and like close to half your weight, depending on how your mass is distributed. And then as you do the push-up, the weight that you're lifting slightly decreases depending on your arm to like body length ratio. It could decrease more if your arms are really long compared to the rest of your body, or if you have short legs or just a short body, it decreases much more. But then going back to like the vertical push-up, lifting your entire body weight, if you wanted to lift more weight during your push-up, lift your legs higher and higher so that you're getting into the more and more weight approaching your full body weight.
Yeah, you want to change the angle to be as small as possible between you and the floor.
Well, even going negative, I'm saying like lift your feet up like above your hips and then do the push-up from there.
Right, which would still be as small as possible, right? The magnitude is greater, but it's more negative.
Yeah.
The smaller that angle, the more weight you're going to lift.
Got it.
Yeah, so if you are interested, I sent you a Google Doc or a Google Sheet.
Opening now.
That has, so I have access to, it's called a force plate. It's just a high-tech scale that will plot as a function of time, the force that's on the scale. So I started, you're in, okay. If you click on the force standing tab.
I see.
See, that's just me standing on this plate.
Yeah.
I'm roughly 1,000 newtons. Please don't calculate that weight. Just let's leave it at 1,000 newtons. You don't know what that means.
That's nice that it's such a round number because you are just smack on 1,000 newtons.
Yeah. And then so that's my starting. Then if you go to force push-up.
It's funny, you could say like with the force of 1,000 newtons, it sounds super fancy and scary. But
so one Zach.
Yeah. Newton is only 1,000th of you. A millizac is a Newton.
There's actually a unit. I learned this from Wolfram Alpha called a Zach. That is 1/10 of a cubic meter, I believe.
Huh.
Yeah. So to these plots, and we'll post these plots in case you want to see what it's like when you do a push-up. Mm-hmm. But so if you go to force push-up now, you go to the next sheet, you'll see me doing some push-ups. So let's see.
I see three horizontal regions, like kind of plateaus of the data. Is that what I should be looking at?
Yep. Yeah. So what I did is I went up, or I started in, maybe you could tell me, but I started in A position, held it for 5 seconds, moved to the opposite, and then went back to the other one, holding each one for 5 seconds.
So based on what we were saying, the less weight situation is when your arms are extended. So it looks like you started with your arms extended, and then you dropped your arms, and then you increased your arms again to being extended. And then you also kind of said that earlier, you explaining the way you do push-ups. But based on the data, it starts low and then it goes to a plateau that's higher, and then it drops to a low plateau again. Like a plateau around 550, and then a plateau around 650, and then a plateau around 600.
Yeah. So this is, so when I started out, I started out, up. Yeah. And it's about 575-ish.
Yeah. Okay. Right.
So
over 550, but not 600. So,
okay. But my question then is we're really...
That's actually a bigger difference than I thought it would be from like let's say 575 to 650. What percentage of change is that? That's not nothing. I thought it would be a lot smaller effect, like the difference between the bottom and the top of your push-up.
650 minus 575. Oh gosh, that's 75 newtons. Divide
a percentage of 575. Let's say 13%. Huh.
Yeah. So it's a difference for me of 17 pounds.
Yeah. Yeah. That's definitely more than I thought it would be.
But I have a quick question for you though.
Yeah.
Because I think something's amiss here somewhere that I'm wondering about. Mm-hmm. Is, okay, we said it should, when you're flat, it should be half your weight. So that's the...
Yeah, assuming your mass is distributed evenly across. Right. Yeah.
Okay, so but what's going on here? Because when I'm flat, I'm not flat. I'm 6...
Pretty close, yeah.
50. Okay, but I'm never, this is all more than half of my weight, the whole thing.
Yeah.
Right. When I'm up in my position. So half my weight's 500, but it's about 575 in my up position.
Right. We expected when you're in your down position for it to be half, and it's 650. I think that just means that you have a lot more weight, like above, like your hands are supporting more weight than your feet by like kind of a lot. Yeah, so your feet are only supporting, if your hands are supporting 650, your feet are only supporting 350. Right.
So my mass, is not evenly distributed.
And we're also, I mean, we haven't said anything about the head, like our head. We can watch Jerry Maguire and see how much a human head weighs. It's not nothing, and it's all like beyond your hands, right? Shoulders, I'm assuming your hands are at your shoulders.
Yeah,
that's something we haven't talked about. Is what if you moved your hands above your head and did a push-up? Is that even possible? I don't know if your muscles would let you do that. Or like if you move them like a little bit forward or a little bit backward, is that an easier or harder push-up? I mean, now we're getting into like the physiology of like what your body can do, which I don't know if you can do that. Because we haven't said anything about like hands together versus hands, separated a lot versus directly under your shoulders, which I think is like a standard push-up. Is kind of what I've been going with. It's like a standard push-up with hands under your shoulders. That's it.
Right. Yeah. That's what I tried to do as best I could here.
Yeah. So even if your body was evenly distributed, its mass, the fact that your forward part, like the part that's doing the pushing on your, like basically your hands are automatically holding up more, even if you're evenly distributed, because you have your head above your hands.
Right.
Like your hands aren't at the very top of your body.
Right. Yeah. So no matter what, there's always, it'd be like, evenly distributed below some point, and then just like imagine you don't have a head, right? You are like evenly distributed somehow.
Right.
It'd be like taking like a little bucket and putting it on top above your shoulders, kind of. That's kind of like what we're imagining. Right. Your head is always adding some little bit that's mainly going to be incorporated in your hands.
Right. Right. Exactly. So you're wondering why it's so much more than half your body weight, the 650?
Yeah. So I
think it's partially your head, and then partially I think just human bodies are not evenly distributed.
Right. Well, so here's what my original thought was. So I'm 2 meters tall, almost to the T. I got like nice round numbers.
To my body. 2 meters tall. You were meant for the metric system.
Yeah. I measured my belly button to be 125 centimeters off the ground.
Okay.
So my thought was maybe it's some ratio or of those sets of numbers that could describe this, why it's more. Because if my mass were directly over, or if my center of mass were directly at 100, then I feel like we'd kind of more or less expect, what we're saying. It's like, okay, imagine you have a board hanging from a rope tied at each end, right?
Mm-hmm.
And you set a big heavy bucket in the middle,
mm-hmm.
but then you pick it up and you move it closer to one end of the thing. And then you move it closer, you're going to expect that the rope that you're moving it closer to is going to have more tension in it. It's going to get more taut as you move that bucket closer to it.
Right.
And it's the other one's going to get a little less. So, if my mass was exactly at 100, it's going to be like the bucket in the middle. It's going to be equal tension on both ropes. But since it's closer to my head, I'm going to move the bucket more towards that direction. And so I feel like it's going to be some ratio of that. And so let's see, how's that possible? Okay, I guess it is. So when I did that, I looked at, so I have 125 centimeters beneath my center of mass, roughly, if that is my belly button is what I'm calling it,
mm-hmm.
75 above it. I would think, so the ratio is like 1.6, 1.7. So that's a little bit, if you take 500, half my mass, and multiply by that, we're roughly getting there. It gets to 800.
Yeah. 800.
Yeah. 800 newtons. So if I said, just to say that again, but more succinctly, if I said the center of my mass is my belly button, I have 125 centimeters below it and 75 above it. And I'm thinking that the force that I'm going to be lifting with my hands is going to be some ratio of those two numbers, what's above my center of mass and what's below it. So when I did that, I got a ratio of 1.7. And so if I was doing 500 would be the halfway point times 1.7 is roughly 800. So that might be what's accounting for it then essentially. Or there's, I think your head would add even more to that.
Right. Yeah, I'm working out the forces real quick. So if you work it out, I got 625, ignoring your head. And the way I did that is just a free body diagram. Your force of your hands up, force of the feet up, your weight down. So up plus up minus down equals 0.
Right.
And then set up a torque problem. This is like basic mechanics, statics problem. Put the pivot point at your hands, and then you have your weight down 75 centimeters from that point. 75 centimeters from your hand should be your full weight, which isn't totally true because your height of your head, drops that a little bit less, but it's close enough. And then, so that's one torque. What? Go ahead.
Actually, does it though? Because wherever your center of mass is, that's where you can calculate the torque from, right?
Well, we don't want to calculate the torque about the center of mass because we want our weight in the equation.
Right. I guess, sorry. What I'm saying is if we're considering we're considering me as a point particle.
We're not anymore though, not if we're doing torques.
Okay.
Yeah, I'm considering it just like a long board.
Okay.
So you have an up force at the pivot point of your hands. I'm calling that a pivot point because what I want is the force from your feet in terms of your weight. And then I can put that back into F equal ma to calculate the force of your hands, which is what this scale is reading, right?
Right.
Yeah. So 0.75 times your weight is equal to, so that's one torque. The lever arm is 0.75 times the force itself, which is your weight. That's balanced by the force of your feet times its lever arm, which is 2 meters. So you have 0.75 times your weight is equal to 2 times the feet force upward, right? 2 times because it's 2 meters long. Yeah. So then your feet force is equal to 0.75 over 2 times your weight. Good so far?
Uh-huh.
And then the force of your hand is equal to your weight, but then less the contribution from your feet. So it's your weight minus 0.75 over 2, 0.75 over 2 times mg. So 1 minus 0.75 over 2, I got 0.625 times your weight.
Now let me give you a slightly updated number. So before this podcast, I made a bunch of measurements of my own body for this very reason. Uh-huh. So if we're doing it about my hands and we're excluding the mass of my head, then it should be, it's from my toes to my shoulders is 162 centimeters.
Okay.
So that would be your lever arm instead of 2.
Right. And then your center of mass is, what was it? 162?
Yep.
You have a long head.
Yeah, well, that's actually, it's to the middle of my arm, I guess. So there's a little bit more.
Oh, okay.
If you wanted to round it up to like 167, that's probably more accurate, I guess, add a few more inches.
I got 815.
Oh, that made it larger?
Oh, I did something wrong. I got 772.
Oh, that also got larger.
Yeah.
That would be when I'm flat.
Right.
So, yeah, I mean, like I also measured the height of my chest when I do a push-up, and I got down to about 30 centimeters. So that's not quite flat for me. So I feel like it's a pretty good number.
Yeah. Yeah. It's within the air bars. I don't know what the air bars are, but let's say they're that big.
Yeah.
Good scientific methods of throwing air bars on after you do the experiment.
Right. Can we think about this? Well, okay, we don't have to talk more about this. We don't want. But the other way I was thinking about it, is if essentially we could model this like a tension. I feel like that's a standard physics problem that every physics student does. Is a board hanging from a rope tied at each end, right?
Right.
And so the center of mass, let's just put a bucket at the center. That's exactly what we're talking about when we're flat. And in that case, your intuition really wants to say, and it's right, that there's the same tension in each rope.
Right.
So I feel like that's just another confirmation of that it's got to, when you're flat, it's got to be half. And then, okay, if you pull one of these ropes up, so now the board's at some angle,
mm-hmm.
the thing that's changing the weight is what? That the force, now some component of the force is going to trying to move the board. So let's say you pull the left one up. So the left one is now higher than the right one.
Okay. Some
component of the force is now trying to push the board to the left, right? Of the bucket.
I mean, I kind of get what you're saying in the if the horizontal axis, if you put it in line with the board. Is that what you mean?
Yeah, you can think of it that way too. Yeah. Or, an inclined plane problem if with no friction between the inclined plane and the ground.
Yeah, I guess. I'm not super comfortable saying that there's a component of the force pushing it to the left, but I kind of get what you're saying. You pulled the left string up. Is that what you said?
Yeah.
I think all that's happening is that and we're trying to see if the left string's tension went up also. That's what we think would happen.
No, it should go down. Is that right? Yeah. I mean, I think we're saying it'll go down because maybe this isn't a good model now that I'm thinking a little more about it.
I think it would go up. I think by raising the left string, it's like we're doing, we said it would go down. The way it would go down is you do the push-up. Yeah, I think we're kind of flipping things too much now, because imagine the extreme of the board being completely vertical. The right string, you could cut it and it wouldn't do anything, right? Or is it holding up? Maybe it's still holding up half the weight. I don't know.
Yeah. I went to that extreme too, and I realized there's some weird stuff happening there. So I don't know exactly how that would play out. Maybe that's not a good model.
Yeah,
it's good for the torque, the center of mass description, but I don't think it's good for the full push-up.
Right.
I had a couple of other places we could take this if you want, if you're not looking to wrap up right away.
I'm not. I'm still trying to figure out the formula, the trig formula for what gives us what we want.
Oh, okay.
So we want something that gives us 1/2 when it's 0 degrees. It gives us 0 when it's 90 degrees, and it gives us 1 when it's negative 90 degrees. When we're calling the angle being the angle that we make with the ground while doing our push-up. So it's completely horizontal. You're lifting half your weight, standing up completely. So I call that 90 degrees. Your feet are the pivot point. Standing up, you're lifting 0 of your weight. With your push-up on your hands is doing 0 amount of lifting. And then negative 90 degrees is the inverted, the handstand push-up.
Wait, sorry. Okay, when it's positive 90, it's 0. Is that what you were saying? Okay,
that's right.
Damn it! I thought I had it for a second. Minus sine x plus 1/2 is almost there.
I think I got it.
Okay.
And it's got to work out to something. There's got to be trig identities galore in here, but this does work. You ready?
Yeah.
Do you want it, or do you want to try and figure it out yourself?
I'm about to mathematically do it, but if you spit it at me.
Sine squared. Did you have a sine squared?
I'm not there yet.
Oh, okay. Sine squared of negative 2 theta plus 90.
Negative 2 theta. Okay, is that plus 90 is not times by negative 2?
That's right.
I'm going to plot it just for the heck of it. Minus 2x plus... Oh, sine squared. Okay, there we go.
And it could be, sine squared of 2 theta minus 90. Maybe that works also. I think it does. Well, it'll give you the same thing, but the way I came about it was to get it in that form. But I think mathematically it would work.
But it doesn't go to 1 when you're at negative 90.
It doesn't? Negative 90 times negative 2 is positive 180.
Plus pi over 2. Or plus 90.
Oh, so that would be plus 270.
Which is 0.
No, it's not. No, that works. Sine of 270 is negative 1, and then squared is positive 1.
Oh, the y component. Okay. What am I looking at then? Oh, okay, wait. Okay, is that where the problem is? Okay, I just plotted it. I'm trying to look at it. So, okay, when it's 0...
When theta is 0?
Yeah, you get 1.
When theta is 0... Oh, yeah, that's right. Damn it. How did I do that wrong? Oh, I see what I did. I did the inverse of what I wanted to do. So it's, ready?
Uh-huh.
Sine squared of 45 minus theta over 2.
Minus theta over 2?
Yeah. And the over 2 doesn't go... It's only under theta, not 45 minus theta. I think that works.
Oh, uh-huh. Yeah, I think I'm going to be getting there in...
It's not as intuitive as I would have hoped. But I see what we're going to get at is a function that we could figure out. If I wanted to lift X amount of weight, what angle should I put my feet at?
That one is doing... This is negative. So what I'm trying to do is take that problem that you did, the bridge problem.
The bridge problem?
Yeah, when I'm supported by... Ooh, that just hurt. My feet and my hands, and I'm horizontal, and my center of mass is not centered.
Not in the middle. Yeah.
So I'm doing that, except I'm putting it up at an angle.
Ooh, that's tough without it being exactly a half. That function doesn't work. Without your center of mass being in the middle.
Which function? The
one I just told you, sine squared stuff.
Oh.
Yeah. So I came at it, initially I came at it just from thinking about the limits of being 0, a half, and 1 in the different positions. But I could do it in the general case.
Oh, I did something wrong.
That's interesting. I don't like that.
Did things cancel?
Yeah.
Okay, I think we did the same problem.
I got something that doesn't depend on the angle, which is not good.
Yeah, that's what I got too. I had 2 cosine squared terms, and they went away. See this?
I don't understand what the hell's happening. Oh, got it. Yeah, it looks like you and I are doing the same thing. But why do you have cosine squareds?
Because I did. So
what's I?
Where's an I?
The far left. I equals.
Oh, tau.
Oh, tau equals. Got it. Yeah, so we did the exact same thing, but I had cosine, not cosine squareds.
Because I did the component that's perpendicular to my body is NH cosine theta times R times the sine of the angle between that, or between,
You double counted the, either it's the full force and the full lever arm times the sine of the angle, or it's the perpendicular component.
Right.
But then it's not times the angle again.
Yeah.
Yeah, so you and I have the exact same thing without the squares.
Right.
And yeah, they disappear, which is not good.
Right, which is why what the heck is going on? Does it have something to do with, we both took the force to be, if you follow my picture, essentially that would be my shoulder where I drew the NH.
Yeah.
And hand would really be at floor level.
Yeah, I had the exact same thought, and I wasn't sure how it fit into this.
Well, put your normal force there, and you're summing torques around NF, I'm guessing, around your foot?
No, I did it around the hand, because I was trying to use some of the forces to get the force in the hand. I see what you're doing, though. You tried to get... I guess that would have worked, too.
Oh, I did the foot, because then that component cancels away, and I only have the hand left, and the lever arm was 0. Well, good to know. We did it 2 different ways.
Yeah, I did it the way I did it because of what I tried earlier. I did something else before that did it that way, so I just tried to modify that equation.
So this distance here is really, I think that's it, Derek. I think as soon as you drop it down to the floor, then you get another component because the lever arm, if I look at if you're doing it between the foot, is now R cosine theta instead of.
No, but we're going to be double counting again. No, I don't think that's it.
Wait, no, why would that be double counting? Oh, because the force then is.
I think you're going to end up with the same thing.
Oh, I think you're right. Yeah, because the force now is already in itself perpendicular to.
You took a perpendicular component of the lever arm rather than the perpendicular component of the force. Yeah, it should give you the same thing either way.
What are we missing here? Because it very intuitively, I think the best thing you said was the go gadget arm thing, right? Like super intuitively, it's going to get lighter. You're going to put more weight on your feet.
So I think we're getting into like the way the body works now. Because think about it this way, like go from a push-up and like imagine you had Inspector Gadget arms, stretch them out and start standing up from a push-up. Like what do you do? You shift, like you physically shift your weight to your heels, like the back, like towards your feet, right? You're not like you could stand up with extremely long arms and kind of walk like I'd imagine like some kind of gorilla or like some ape, right?
Right.
With really long arms, and technically you have really short legs and your arms are really long and you're kind of doing this knuckle dragging thing, supporting yourself on four limbs in this kind of weird upright or at least like a push-up kind of position, right?
Right. Okay.
But we don't do that. We actually like when we get close, we start to shift our weight back over our feet. So I think the answer is that our feet aren't point like spikes on the ground. Like there's some stability length that allows us to stand upright without using our arms, right? Like it's a stable equilibrium. It's not unstable. So there's some kind of like range of tipping that we're allowing ourselves. And even like stand up and then bend over and touch your toes. Like your center of mass still stays over your feet because you like push your butt out, right? You push your butt behind you and your head goes in front of you, but you keep your belly button over your toes, like within that stable range. So I think if we didn't do that, then what you and I are doing with our free body diagrams and torques, if we were actually a rigid board that couldn't like bend at the hips and like kind of shift our weight in a way that we don't actually mentally even think about, but it just happens, I think we are right that it would do this. But since we've done a stand up and sit down motion and touch our toes and everything in between, our body kind of just adjusts subconsciously almost. Like we kind of just automatically move our center of mass over our feet and don't use our hands. Like imagine if we had skis, like really long skis.
Okay, all right.
You could lean forward really far without touching the ground with your hands.
Right. You can Michael Jackson it up.
Yeah, exactly. So I think maybe that's where we're getting tripped up.
So
it's like there's some sort of shift of the center of mass, either backwards. I think it's backwards, like towards the feet as we start lifting ourselves up. I don't know. I'm not super happy with that answer, but
so we're saying because when we did this little model, our angle calculation fell out. That you're saying, what it ends up with being is what's important is the ratio of your body length and your center of mass. So you're saying because we based on my data, we still know for sure that it's changing, that it's got to be then our body center of mass to that's shifting. So our body length isn't changing.
Right. Yeah. Something like that. I don't know. I'm not. But what this means though is that as you do a push-up, the force shouldn't be different between the lower and the upper portion of the push-up, which is what on the scale you saw that definitely changes by quite a bit, by 15%, 20% almost.
Right. Well, yeah. So it's got to be your center of mass that's being shifted somehow.
Is it because the distance, like imagine you were on maybe not skis, but something kind of longer, like clown shoes, and you do a push-up and your heel pushes back behind your toes as you pivot around your toes? It doesn't seem like it would affect that much.
I'm still go back to your original, where we started. You have the center mass. You're doing one of the handstand push-ups, and your center mass is above your hands now,
right? And
then you walk out away from the wall a little bit
with your hands.
Yeah, you're intuitively you're gonna be doing less of a push-up, or like there's gonna be less weight,
right?
Now, but we're saying the angle doesn't matter.
Yeah. But yeah, I don't know.
Yeah, I think I'm gonna have to like think about it more. So,
Yeah,
so I feel like
I'm surprised that the angle just dropped out. I don't really get why it did.
Right, because of your initial thing, we know that okay, if it was totally based on the ratio of your body to center of mass, right? That's what you ended up giving me or saying? Okay, what was your final equation for your normal to the hands?
Like if you were just holding yourself up horizontally?
Or the one that you just derived.
Oh, with the sine squared?
No, from your free body diagram there that you said where we both got the same thing with the cosines.
Oh, I didn't work it out completely because I saw the angles dropped out and I was like, well, I don't know. I'm stopping.
Well, but once the angles drop out, isn't it?
Oh, what is it then?
There's only one couple other things, right? That's left.
Yeah.
What I'm getting, and this could be wrong, so I just want to verify, is that it's your weight times your center of mass over your total body length. Your
weight times center of mass over your total body length. Yeah, I got the same thing.
Okay. That would mean then, we're missing something, because that would mean when you're standing up and it's 0, your center of mass is on the floor. Or when you're vertical and it's, standing on your hands and it's 1, your center of mass is at your feet.
Right.
That's not happening.
No.
I'm wondering if it has to do with our foot, that, you and I both said, okay, we're at some pivot point there at the bottom. But I'm wondering if for some reason it has to do that we're not really a triangle. We're more like if you cut the tip of a triangle off.
Right. Yeah. Some sort of quadrilateral.
Yeah. We're quadrilateral, but that looks
that's kind of what I was saying with the clown shoes. Like by doing the push up on your toes, you're like pivoting around your toes, but your heels pushing forward and back.
Right. But that's not enough to...
That's what I was saying.
It's got to be angle dependent. Somehow we're missing something that's right. Getting rid of the angles. There's got to be an angle dependence in here. Otherwise, I mean, A, just intuitively, it's got to be that. B, like your center of mass might move some, but it's not moving so much that it's going to put all your weight, it's not moving to your feet ever.
Right.
So that says to me it's... your center mass may move, but it's got to be dependent somehow on the angle. And yeah, if maybe it's from this, it kind of looks like a gorilla now that I'm looking at it, like you said.
Yeah, right.
Our gorilla lateral? No, that was bad. That was awful. Quadrilla? Yeah. I mean, I feel like at this point we should stop and we can figure it out over the week, unless you're like really gung ho on.
No, I got the spark of something, but it's not going to be complete in this recording. I can tell that.
Okay. Well, yeah, I think this is a good place to stop then, because we did our mission, right? We said, this is what we think. We tried to work it out a little bit, and again, we're stumped.
Right. Yeah. Well, I mean, we did it intuitively, and we kind of just like argued through some limits, and we came up with what I think is the right solution, and that your push-up gets less and less of a force as you go through the push-up from starting at the bottom to increasing the height above the ground. You're pushing less and less of your weight up. Roughly a half, probably a little bit more than a half of your weight. And when we sat down to do the free body diagrams and Newton's laws, things fell apart because it became not angle dependent.
Right. Yeah.
And we think we're right on the angle dependence because of your data with the force plate that you showed that when your arms were extended, it's holding up less weight than if your arms are not extended.
Right. Yeah. It's an empirical fact.
Right.
That it changes when you're from the up position to the down position.
Right.
Then
by like 20%, I think it was like 16 or 17%. Like it wasn't nothing. It's like a pretty decent amount of difference.
Yeah, and so it could potentially be that your center of mass is moving for some reason, but it doesn't move that much. No. It doesn't move 20%.
Right.
So that's not the reason. There's got to be an angle dependence.
Right. We wanted an angle dependence of the force of the hands that are holding up your body. And going through Newton's laws in our simple model, it failed. The angle dropped out, canceled out. Nothing was angle dependent. So, yeah. We're stuck. We'll stop here. Listeners, try it yourself. Tell us where we went wrong. And we'll try and figure it out as well.
Yeah. Good luck. Happy free body diagrams.